As an example, using the chain rule, z is going to equal f of xy equals x squared plus y cubed. X of t will be the cosine of omega t, y of t 2 times the sine of omega t. We can write the derivative of z with respect to t, which is the same as derivative of f with respect to t. Either notation is all right once we've made this definition. And we write the chain rule for that function. Just the chain rule for general function f of x, y, where x and y are both functions of t. And we take each part of this expression and evaluate it. This is very straightforward. The partial derivative of f with respect to x is 2x. Partial derivative with respect to y, well, we have a plus y cubed. That's going to be 3y squared. The derivative of x with respect to t, well, x is a cosine of omega t. And we get a straightforward derivative here, negative omega sine omega t. The derivative of y of t is 2 times omega times the cosine of omega t. Those are all straightforward derivatives that you should be accustomed to by this point in the course. So we won't get into any discussion on that. We're simply going to turn the crank and evaluate this partial derivative. So the partial of z with respect to t is, of course, the partial of f with respect to t, etc. Term by term, partial of f with respect to x is 2x. Partial of x with respect to t is negative omega sine of omega t. It looks like I've got a parenthesis that needs to be closed. And then the partial of f with respect to y is 3y squared. Partial of y with respect to t is the 2 omega cosine of omega t. So this is just a matter of doing some simple calculations and substituting. Now we can then substitute our expression for x to get this partial of z with respect to t purely in terms of t. So our x is the cosine of omega t, so we replace x with the cosine of omega t. Y is 2 sine omega t, so replace the y with 2 sine of omega t. And the expression continues. Now I think I've lost a piece of paper here that I was using to obliterate a mistake I made earlier. Let's get that back in place. Simplifying this or multiplying things out, we get these expressions. I sneaked this omega in here because I nearly missed it. And I did have a 12 here. And that's why that little piece of paper is there. And that 12 just came from a little careless mental arithmetic. Multiplied 3 by 2 by 2 and got 12, but this 2 is squared, so it gives us another factor of 2, gives us the 24. And we then get this expression, simply factoring out a negative 2 omega, factoring out a 2 omega, fairly straightforward. Having done that, we recognize that we also have a cosine of omega t and a sine of omega t common to both terms. So we could write this finally as 2 omega cosine of omega t sine of omega t multiplied by negative 1 here, and factoring out the cosine of one of the sines, we then have 12 sine of omega t. And that completes the calculation. Now, this can actually be interpreted geometrically to an extent, and we're going to take a quick look at that.